Hi class, welcome to the next section, chapter 9.3. Today we're going to talk about three-dimensional coordinate geometry. So what we're going to kind of focus on here in this section is really just expanding the idea of our graphing capabilities and our spatial abilities. We're going to start talking about things in three dimensions, right? So we know that our regular everyday lives are spent in three dimensions. We are not in a 2D world, right? So 2D is really up, down, left, and right. So now we're going to add a third dimension, which is an in and out sort of dimension, so that we can talk about things and draw three-dimensional figures, okay? So a big part of calculus, mainly calculus 3, is focused on math in three dimensions. So we're going to see a little bit of that here in this chapter, and it'll help you to sort of try to start to visualize things with an extra dimension. It's very, very useful, very common thing that we do, especially in calculus 2, way more so in calculus 3 that we deal with three-dimensional stuff. Okay, so again, what we're trying to do now is we're going to introduce a new axis. So in order to do this, what we're going to do is we're going to think of our regular XY coordinate system, right? And what we're going to do is we're going to, instead of thinking about it as like us looking at a piece of paper, right, up, down, left, and right, we're going to take that XY coordinate system and we're going to lay it flat on the ground, okay? And then what we're going to do is we're going to introduce a new coordinate system, which is an up and down. So what do I mean by that? We're going to take our XY plane, we're going to lay it on the floor so that our X, instead of moving left and right, it now moves in and out, and our Y, instead of going up and down, is going to go left and right. Okay, so Y-axis moves left and right, the X-axis moves in and out, and we're going to add a new axis called the Z-axis, which is going to move up and down. And so those three together will give us a three-dimensional coordinate system. Okay, so again, my X and Y, instead of being regular X and Y here, I'm going to turn it and lay it down on the table. So now this is X, it goes in, right, inwards and outwards, and it goes, Y is going to go left and right, and our Z is going to move up and down, right? So our X-axis in the, I guess we could call this the out direction towards us, or in, I guess, this is the positive direction. This is the negative direction. For Y, this is our positive direction. This is our negative, just how it was before, where this used to be X, it's now Y. Z downwards is negative, and Z upwards is positive. Okay. So if we want to plot a point in three dimensions, we use what's called an ordered triple. So before we were using an ordered pair, right? It was an X and a Y. Now we just have a third term, which is Z, which is the last term. So just like in two dimensions, we had A, B, C, D, X, Y, right? That's the order that we moved for two dimensions. So for three dimensions, it goes X, Y, and then Z. It just goes in alphabetical order, right? X, Y, then Z. So let's do an example. If I want to plot the point 2, -3, 4, that means my X value is 2, my Y value is -3, and my Z value is 4. So we take our X, our Y, and our Z. We move 2 in the positive direction of X. 1, 2. Then I move -3 in the direction of Y, so not this direction, but this direction. So I go 1, 2, and then from here, I move 3 in the negative direction. And then I will move 4 units upwards from that point. Okay, so I come down to, I move over -3 units, and then I will move up 4 units. And that is my point in space. Okay, so I don't know if you've noticed before, hopefully you have, but when we have a point in R2, that point actually makes a rectangle, right? We go over X and we go up Y. That forms the basis of a rectangle for us. In R3, we have a left, an in and out, or left, right, an in and out, and an up and down, and that actually forms the basis of a prism for us, right? So the X, Y, and Z axes are part of that prism. And then we have how much we moved over to get to our point, right? So I can, if you look at this, this looks like a prism, right? It's a cube. Prism is a cube. right? For all intents and purposes. Okay, so just like in regular x and y, this point here would create a rectangle for us. In the three-dimensional system, it is a prism. So we have 2, -3, 4. I started off by moving in the x direction, and then the y, and then the z, but I actually could have moved in any direction from here. I could have started at the origin and moved up 4, and then -3, and then in 2 units and gotten to my point. Okay, I could have moved up to 4, in 2 units, and then over 3 units, right? I could have started here and gone in 2 units, up 4 units, and over 3 units. All of these are actually paths to the same point, right? I could have went over y and then done my x and then done my z, right? But what I followed for our example here, right, was that I went x, y, and then z, but I could have actually went in any order as long as I'm moving 2 and x, -3 and y, and 4 and z. Okay. So again, note that each route along the edge of this prism is a different pathway for me to get to the point 2, -3, 4. So pretty much everything that we do in our regular xy plane, our xy coordinate system, is exactly the same in 3 dimensions, except that we add an extra value of z. Okay, so things like distance. Distance is calculated the exact same way, but instead of the distance between the x's and the difference between the y's and the difference, and then, you know, squaring those and adding them, taking the square root, we just added difference of the z's, right? So everything is just a little bit different. Okay, so for example here, the line y equals 2 and x and y is a line, right? Y equals 2 is a constant line that moves left and right. In 3 dimensions, it's actually a plane, right? It's a whole xy sort of equivalent, but it's at the value that y is always 2. Okay, so here we have the line y equals 2, but in 3 dimensions, it's actually a plane such that y is always 2. So here I can have any value of z and any value of x, but y is always at this value of 2, right? So it's a plane. It goes in this direction, infinitely, and it goes up and down infinitely. So instead of it just being a line, it's a plane. Notice, however, though, remember what we talked about for the x, y plane, right? My x and y plane, I'm thinking about this as me laying it down on the floor and then adding a z direction. So imagine if I could look down onto the xy plane. I would see this, just a line, this line, right? Because there is no depth. I can't see that this plane actually has like a front side, right, and a back side, like I can in 3 dimensions. So when I expand this into 3 dimensions, this line is actually an invisible wall that I'm looking down onto, right? So in 2 dimensions, it looks like a line, but in 3 dimensions, I can see that it's not actually a line, it's a wall, right? It has a front side and a back side. It actually doesn't have any front or back because there's no width here, there's no thickness. It's just an up and down, and, you know, x in the positive and x in the negative direction, okay? But here in 2 dimensions, there is no out, right? There's no up, right? Up is considered y axis here. So if you can kind of look at it and think about that as a connection, right? If you think about my 2-dimensional system is me just looking down on xy and looking at the top of, you know, what would be a wall in this case, right? So that's the relationship between x and y, is that a line here is actually a plane here, okay? We do have lines in 3 dimensions, and we'll talk about that I believe in the next section or the section after that. But we do cover that in chapter 9. So the rest of what we do in chapter 9 is really focused on 3-dimensional systems. But first we have to get familiar with, you know, a line versus a plane versus a point versus, you know what I mean? How do I plot things in 3 dimensions versus 2 dimensions? Understanding that there's an extra sort of aspect for me to take into consideration here. Okay. So again, this plane contains all points on the graph such that y equals 2. Okay, so here y is fixed at 2, and then I can choose different values of x, different values of z. So again, the distance between 2 points in 3 space is pretty much the exact same way we calculate it in 2 space, except that we have to take into consideration that extra variable. So let's say that I have 2 points in space. Let's call them P0 and P1. Okay, P0 is given by X0, Y0, Z0, and P1 by X1, Y1, Z1. So the distance between these 2 points are the differences in their respective variables, right? Inputs, their values, squared, add them together, and take their square root. Okay, so the distance between P0 and P1 is the difference in X values squared plus the difference in Y values squared plus the difference in Z values squared, and then take that sum and square root it. Okay. So similarly, we have the equation of a sphere. So we're in 3 dimensions now. So the equivalent of a circle in 3 dimensions is the sphere. Okay. The equation is very, very similar. A sphere that is centered at the point ABC that has a radius of r is given with this equation. So we have x minus a squared, y minus b squared. Here we have z minus the z center value squared equals r squared. So the only thing we're really doing is taking into consideration that extra term. Okay. The way we work with this is the exact same way we do it in all the other times. I take my equation. If I need to, I complete the square, right? So if I want to find the equation of the sphere that has this equation given, notice it is not in a standard form. I don't know what the radius is. I don't know the centers. So what I need to do is kind of just group my x's, y's, and z's together and keep my constants on the other side, complete this square as needed so I can figure out what my zeros are. So let's start to manipulate this. I don't have any, I can move this 2x over, I can add this y over, place it close to this y, and move this z over and keep 8 on this side, right? So we're going to complete the square. So before we do that, we try to get our x's together, our y's together, and our z's together. So remember, to complete the square, you need negative b over 2a squared. So here we are going to have basically just, we're going to add and subtract the 1. Here, negative b over 2a gives me a 1/2. I square that, I get 1/4. So I'll add and subtract the 1/4 here. Here I will have negative 3 over 2a, so that'll be 3/2. So I will add and subtract 9/4. Okay, so here, add and subtract 1. For the middle term, add and subtract 1/4. The last term, add and subtract 9/4. Okay. I have 8 on the other side. Remember, I just need the first one, whatever the positive one is, right? The positive one and the positive one. So the negative one, negative 1/4, and negative 9/4 all get to move to the other side of the equal sign. Okay. So all I've done is I have my 3 terms, my 3 terms, my 3 terms, and then all of the extra constants over here. I'll add these together. I'll finish factoring these into perfect squares. So this is x plus 1, y minus 1/2, and z minus 3/2, right? Squaring each term. I add these together and I get 83 over 8. Before we go that far, this is the equation of my sphere, right? I have my center. My center is at negative 1, 1/2, 3/2. And the radius is whatever the square root of 83 over 8 is. So let's add an extra dimension to that. Let's say I want to know what the trace is by intersecting this circle with the plane, or the sphere, I'm sorry, with the plane x equals negative 1 plus 1/4, the square root 1 or 2. So you might say, why the hell do we have this crazy looking thing? Like, what kind of a question is this? That's because it ends up being nice at the end, right? That's the reason why we have this. I could have very, very easily said, what happens, what's the equation of the intersection between this sphere and the plane x equals 3, right? Very, very easy for me to do that, but we would have ended up with a really messy answer. So here, this is actually going to come out nice for us, right? So I have my sphere, okay? This dot is located at negative 1 on x. Okay, so you go back 1 on negative x, positive 1/2 on y, okay, and then up 1.5 here. So you might say, well, that looks like it's at 2. Well, that's because it's kind of over to the side and pushed back before we go up. So the dot never lines up with the exact values. You have to remember this axis value is slanted. Very much so like we had in the beginning, right? Everything is slanted. So this point looks like it matches up with 3, but it's really at 4, right? It's down a little bit because I had to come down and over and then up. So, right, come over and then down after I went up. It all makes sense. It is never going to be, oh, it's -1, -1, and 4, and you just plot a point there. You have to go with the skew that you have, right? So, okay, so this is my point. So here we have a slice at x equals -1 plus 1/4 root 102. So square root of 102 is somewhere around 10, right? So this is basically -1 plus 10 over 4. So it's not too much more than 1. So it's pushed forward a little bit. I know it's hard to see exactly where this intersection is, but it's a little more than 1. And here, I know this looks like an oval, but that's because we are tilted a little bit on the x-axis. This is really just flush with y, but it's actually skewed quite a bit. So this is where the center would be if we were able to, we'll find this once we find the equation, okay? And the intersection with this plane is a circle, right? So if you intersect a sphere with the plane, you will always get a circle out. I know it looks oblong, but that's only because we're actually tilted a little bit. It's just hard to tell that we're actually tilted from this, what we would consider straight at this point, okay? So what we're going to do is we're going to take x and we're going to plug it into our value of x. So I got this crazy thing here being squared plus y minus 1/2 squared plus z minus 3/2 squared equals 83 over 8. We obviously want to simplify this down and move it over to the other side, and you should notice that we have an equation in y and z, which we should, because this plane is centered on x, right? So the movement is in y. Remember, the left and right now is y, and the movement up and down, which is z, right? It's fixed along the x-axis. There is no movement anymore in that direction. So it makes sense that our final equation will be y shifted somehow squared and z shifted somehow squared, and then a new radius. The new radius will be found by plugging in this x into my equation. So let's notice that I have a -1 and a +1 on the inside. So those two things will cancel each other out, and I'll be left with 1/4 square root 102 squared, y minus the 1/2 squared, z minus 3/2 squared equals 83 over 8. So let's go ahead and square this term, okay? And we're going to end up with 102 over 8, which will simplify to, over 16, right? So the 102 divided in half is 51. 16 divided in half is the 8. I can now subtract this, move it to the other side. So I'll have 83 minus 51 over 8, which is 32 over 8, which gives me a value of 4. So I actually have a very nice circle here. The center's a little bit off, right? But that's not anything different from my original circles. It's just that now it's a circle with radius of 2, centered at the same y and z values as before. So this is just moved laterally along the x-axis. It hasn't moved left or right at all, or up and down. It's just moved in position along the x-axis. So it's still at the center. It just happens to be now towards the edge. It's not all the way at the edge of the end of the circle, but it's, you know, somewhere kind of in the middle. This should be cutting my circle off at some point. If I was a little bit better at graphing this stuff mechanically with the codes that I used, I would have separated this with some dashed lines, but it was a little too advanced for me, so I didn't get that accurate here. But just know that this is cutting my my sphere at some point. So this is kind of what's left over it, and then everything else is behind the sphere. And this is the equation of that trace. So the trace is the outline of the intersection between the plane and the sphere.